Yep. All right. So I'm going to redo that integration video and kind of break it up into some smaller videos. With this video emphasizing integrating functions that are going to involve arctangent of x. Okay. So let's start with something basic. So we'll say question one here. All right. So the integral of 1 over x squared plus 1 dx, right? So when you're doing an integral problem, really the first thing you should always do is look at the function and say, hey, do I know a function whose derivative is 1 over x squared plus 1? And hopefully you do. All right. So that is arctangent of x. And then, of course, it's an indefinite integral. There are no limits. So it add my constant of integration. So what did I just find? I found a family of functions differing by a constant such that if I took the derivative of this, I would get 1 over x squared plus 1, which should make sense because the derivative of a sum is a sum of the derivatives. The derivative of a constant is 0. That's why you add that. And the derivative of arctan of x is 1 over x squared plus 1. So easy breezy, question 1. I don't know why that wrote in black, but it did. All right. Let's go to question 2 now. Super cheeseball, modification of this. What if I had the integral of 4 over x squared plus 1? All right, so obviously, or maybe it's not obvious, but this should not be freaking you out. 4 is just a constant, and as we know, constants can be pulled through integrals because at the end of the day, the integral is just a limit and a sigma, right? And you can pull constants through that stuff. So I can rewrite this as 4 times the integral of 1 over x squared plus 1. And then, so it's the same thing. So you basically, all right, we just did this. The integral of 1 over x squared plus 1, that's going to be arctan of x. So there's a 4 out in front. So I get 4 arctangent of x, and then again, plus some constant of integration. Okay, so pretty simple stuff there. So you're like, all right, let's mix it up a little bit more. All right, what if it was the integral of 1 over 4x squared plus 1? So 4x squared, written like that, plus 1. How would I do that, right? So now that doesn't kind of look like 1 over x squared plus 1, or maybe better yet, 1 over stuff squared plus 1, right? And so at first glance, it might seem that, yeah, that's not arctan, and maybe you think to do a u sub, but a u sub's not going to help you here. Because if you let u equal the denominator, right, your du is going to have an x in it, and there is no x up top, and usually when you get too much function in the u sub, that's not a good thing. So what is it that you can do? Well, you could use a little algebra here, and you can rewrite the bottom as 1 over 2x quantity squared plus 1. So it's kind of fitting that mold or that form of 1 over stuff squared plus 1. So now there's two ways I can approach this integral here, and I'm going to show you both. The first way would be, all right, I get it. But this isn't x squared, it's stuff squared. So, typically a technique that we've learned in AB calculus is something called a u substitution, where we can let u equal that innermost function, right? We already talked about letting u equal the denominator is not going to be beneficial to you. But if I let u equal here, this innermost function, what's in parentheses, that will be. All right, so think about this. Du would be 2 dx, and I don't see 2 dx, I see 1 dx. So that's not the end of the world, though. This is an equation. I can rewrite this, right? Multiply both sides by a half, as a half du equals 1 dx, okay? So I see 1 dx right here. So all of that becomes 1/2 du, okay? What about this? The bottom is not u. Right? I didn't let u equal the bottom. I let u equal 2x. So the bottom is actually u squared plus 1. So when I rewrite this integral, I have the integral of 1/2 du over u squared plus 1. Now the 1/2 is a constant. We know that can get pulled out. So I get 1/2 the integral of du over u squared plus 1. And you're like, oh, wait a minute, I can do that. Right, we just did that over here in question 1. Right, the variables are dummy variables. Whether it's x, u, y, g, it doesn't matter. Do you know a function whose derivative is 1 over u squared plus 1? The answer is yes, you do. All right, it's going to be arctangent of u. Now, don't forget this half multiplier that you have out in front, and then don't forget that constant of integration when you integrate. This is a family of functions such that if I take the derivative of it, I would get this. So now, obviously, the initial problem didn't have a unit. So you're like, well, if only I knew what u was. Well, you do know what u was. You let u equal 2x, right? So you can rewrite this as 1/2 arctangent of 2x and then plus k. And that is your answer. This is a family of functions such that if I took the derivative of it, and I use the chain rule here because it's a composition, at the end of the day, I'm going to get something that simplifies to that. All right, so solid little problem. I personally would not do this with a u sub, especially if I wanted to get a 5 on the AP test, because when your u is linear, and only when it's linear, you can use what we commonly refer to as the reverse chain rule. There really is no such thing as the reverse chain rule, but when u is linear, you can do the following. So I still would want to rewrite this into this step here. So I'll kind of start with that down here. So I still have to rewrite it so that I can recognize the form of arctangent. Okay, and I would view this as, do I know a function whose derivative is 1 over stuff squared plus 1? And the answer is, I do. It's going to be arctangent of stuff, and then remember, times 1 over the derivative of stuff. Now, stuff is 2x, so the derivative of stuff is 2, so 1 over 2 would be 1 over 2. And then I would get plus k. And obviously this, right, multiplication is commutative, is the same thing as that, and you do it without doing all of that u substitution work, which is kind of unnecessary. All right, so all integrals involving arctan. Let's do one more, which I don't know if they would actually put this on the test, but they certainly could, because technically it is in your curriculum. So let's take a look at it. So let's go question 4 here. So let's do the integral now of 1 over x squared plus 4 dx, right? So that's just like, wow, when the 4 was here, it was no big deal. When the 4 was there, it was no big deal. When the 4 is here, it's not that it's a big deal, but you got to mess with it a little bit, right? So right off the bat, this is not arctan because this is not 1. It's got to be 1 over x squared plus 1. So you got to use some algebra to rewrite this, right? So what you could do here is you can say, hey, listen, I want this to be a 1, so let me pull a 4 out of the denominator. So if I pull a 4 out of the denominator, at first glance, you're like, yeah, but there's no factor of 4 here to pull out. All right, so think about what you would do here. 4 times what gives you x squared? I think you'd all agree 4 times a fourth x squared would give you x squared. And then plus 4 times 1 gives you 4, okay? So again, if you're not believing me, like, wow, what'd you do there? If I distribute this 4, I'm going to get that denominator. Now, why is this helpful? Well, let's kind of take our time. First off, this 4, right, is a multiplier. It's like 1/4 times this fraction here, right? So maybe for note or video flavor, I will go bananas and rewrite this fraction as 1/4 times 1 over 1/4 x squared plus 1 times dx, right? If I was to multiply, that's a horrible 1/4. Let me erase that and clean that up. All right, give that another go. Integral 1/4 times, okay? So if I was to multiply these two fractions, you should all agree that I would get that. Now, I'm not saying this step is necessary, all right, but I just chose to do it because now it's maybe obvious to me that this 1/4 is just a constant multiplier, and as we know, they can get pulled through an integral. So I can rewrite this as 1/4 the integral of 1 over 1/4 x squared plus 1 dx. Now, believe it or not, this now is a lot like this problem here. Instead of 4x squared, it's 1/4 x squared, but it's the same thing. I need this as stuff squared plus 1, not 1/4 x squared plus 1. So, here's the 1/4 out from the problem. 1 over, how would I write this? What squared plus 1? What would I have to put inside these parentheses so that it was equal to 1/4 x squared? Hopefully you would say 1/2 x, right? Because isn't 1/2 x squared, quantity squared, going to equal 1/4 x squared? It is. And so now you're like, oh, so now I can view this as the form of 1 over stuff squared plus 1. And oh, by the way, stuff is linear. And when stuff is linear, that means a u sub is going to work, and we're going to kind of do that u sub in our head, right? Like I did the second time in problem 3. So I have the 1/4 out here from this, And now, do I know a function whose derivative is 1 over stuff squared plus 1? I absolutely do. It's going to be arctangent of stuff, don't mutilate stuff, right, times 1 over the derivative of stuff. So the derivative of a half x is a half. So I would get that. And then plus c. Well, 1 over a half is 2. 2 times a fourth, right? Maybe I'll even write it this way. Take our time. It'd be 1/4 times 2. Arctangent of a half x plus c. And then 2 times a fourth ends up being a half. So I get 1/2 arctangent of 1/2 x plus c. All right, and there I go. So I gave you kind of 4 different variations of how you can see potentially arctan appear in an integration problem. All right, so I'm going to stop the video here, and then I'm going to make another video with some other twists and turns about this.